Okay, so today we are covering chapter 8. And chapter 8 is all about the comparison of paired samples. Okay, and so we'll learn a few tests. In particular, we will learn the paired t-test, also a confidence interval for a mean difference, we'll also learn a couple non-parametric tests, the sign test, which is non-parametric, and the signed rank test, which is also non-parametric. Okay, just give me a second here. All right, and so what makes chapter 8, or what separates chapter 8 from, say, chapter 7 is that we are dealing with paired data. And the key here is that, at first it might appear like you have two samples, but the key is that every observation in one sample is paired with an observation in the other sample, okay? So let me just kind of jot that down. Okay, but every observation in one sample is paired with an observation in the other. Okay, and so if this is the case, then there's a few kind of key things, right? Like if your two samples have to be of the exact same size, otherwise every observation won't be paired with another observation. And it actually might be better to think of it as just having one sample, but each observation has two measurements, okay? So think of the data as having one sample, each observation has two measurements. So some common scenarios for paired data would be something like you have before and after measurements. Or you have twin studies. Or you can also have a situation with matched cases where cases from one population are matched with cases from okay. So in a matched cases study, you might not have, it might not be one observation getting two measurements like a before and after situation, but you might have cases from one population that get matched with cases from another population based on demographic information. So for example, you might want to compare one school district with another school district, but then you match your students based on, say, age and gender and maybe income level or something. And so you'll have, you know, a student in a male ninth grade student from high SES matched with another male ninth grade student with high SES. And you'll have maybe a, you know, a eighth grade female with, you know, middle income matched with another eighth grade female with middle income or something. So you might try to match your cases based on demographic information if you're drawing from, say, two different populations or something like that. Okay, and that would be another example of a paired study. Okay, let me folder here. This is week 4 Monday. All right, so let's take a look at an example, and I'm going to use an example from an older edition of our textbook because I like the numbers here a little bit more than kind of the corresponding example in the current edition. So this is kind of our table of data. You don't have to copy this table. But basically, the study, it says, the study says, does drinking coffee affect blood flow, particularly during exercise? Doctors studying healthy subjects measured myocardial blood flow, MBF, during bicycle exercise before and after giving the subjects a dose of caffeine that was equivalent to drinking 2 cups of coffee, okay? And so they look at the baseline values, and then they look at the values after taking the caffeine, okay? And so, so these are the numbers, all right? And so the question is, does drinking coffee kind of affect the myocardial blood flow, right? Or we'll say, does caffeine affect MBF measurements? Okay, and so this word affect is non-directional. It doesn't say, does caffeine increase or decrease or anything like that. So here we are going to have a two-sided test. I know there's a lot of questions on, you know, when do we use a one-sided or a two-sided test? It all depends on kind of the premise of the question. And so here, the question just says, does drinking coffee affect blood flow? It doesn't say that, you know, we're expecting the blood flow to increase or decrease or something like that, okay? So what we will, let me first start off by doing the wrong approach, okay? All right, so the wrong way, all right? So this entire slide is wrong, okay? The wrong way would be to do a t-test for independent samples, which is what you have learned so far. Okay. So, so here to do a t-test for independent samples, our null hypothesis would be that mu1 is equal to mu2, and our alternative will be mu1 does not equal mu2. Okay, and we'll say group 1 will be baseline, and group 2 will be caffeine. After caffeine, okay? So we'll calculate our standard error. Standard error is the square root of S1 squared over N1, S2 squared over N2. We're going to have the square root of 0.83 squared over 8 observations. And again, this is the wrong way. All right, I want to make that very clear that this is the wrong way to approach this. You know, but I'll go ahead and I'll punch all of these numbers in. All right, so we're going to square that. 8. Or 226, so we'll round off to 4 decimal places here. Okay, and our test statistic t, y bar 1 minus y bar 2 divided by the standard error. Let's see what this comes out to be. 5.4 minus 3.99 divided by our answer, 2.721. Right? And then our degrees of freedom is N1 plus N2 minus 2. We've got 14 degrees of freedom. We're going to look up 2.721. All right, so I'll go to my T table. So hopefully this feels familiar, not surprising anybody. And we're going to look for 2.721, and we get between 0.26. So we get the upper tail probability to be between 0.01 and 0.005. Okay. Okay. And because we have a non-directional test, we will double our tail area for our p-value. Okay, so the p-value, so we'll say our p-value is between 2% and say 1%. Okay, our p-value is between 2% and 1%. So if our significance level is 5%, we would reject the null hypothesis. And if alpha were 1%, we would not reject the null hypothesis. Okay, so let me just kind of pause here for a moment and just make sure this This is good with everybody, just kind of this process. This would be taking the t-test for independent samples, which you have learned, but I'm just telling you that if you approach this problem this way, this would be the incorrect way, right? So this is incorrect because we're treating these two measurements, these two groups of measurements, as being independent groups. Okay, we're almost saying like we have 8 random people over here and we have 8 random people over here. Okay, so this approach is wrong. We're treating the kind of two groups as just independent, okay, but they're not. Each measurement is actually related to the other, right? And if you look at each individual, what you'll notice is that the baseline number is higher than the caffeine number in every single one of these cases. Okay, so let's try approaching this the correct way. Okay, all right. So the correct approach is to treat the observations as they are paired data, which they are. Okay, so I'm going to go ahead and just copy my my table here again. Okay, and let me just write the correct way. All right, is to conduct what we call a paired t-test. And this treats the values in the two columns as a pair. And the columns as pairs. Okay, so what we're going to do is we're going to calculate the difference, a column of differences. Okay, so we will say the difference will be baseline minus caffeine. Okay, and then so we'll have the difference. All right, and so I've computed all of these numbers. If you do 6.37 minus 4.52, you will get 1.85. And then going down the column, these are the differences for each thing. 1.88, 1.46, 1.05, 1.67, 1.74, and 0.33. Okay, and then I'll go ahead and I will also calculate the mean. 1.15375 is the mean. And the standard deviation is 0.629. Okay, so here's this, all right? And once you have this column of differences, we could ignore the two original columns, baseline and caffeine. Okay. And so, so now basically we're going to treat this almost as if we just have one sample and it's the column of differences, okay? So we almost pretend like we have one sample and it's a sample of differences. So this time the hypotheses for the paired t-test. All right, your null hypothesis is going to be that the mean difference is equal to 0, and we'll keep it non-directional, and we'll say the mean difference does not equal 0, okay? So very important, please note. Okay, there is only one parameter, right? Only one parameter, mu d. The mean difference. Okay, it is incorrect to use mu1 and mu2. Okay, so don't create a hypotheses with mu1 and mu2. Mu1 and mu2 indicates kind of the existence of two separate populations and two separate population means. Here we're only interested in kind of the difference between the before and the after, the baseline and the caffeine measurement. Okay, and we can see that for all. Especially if there's also a plot of this. Oops, what's going on? Something happened here. Oh, jeez. Here's a plot, and we can look at every individual. All 8 individuals experienced a drop in NBF after taking caffeine. Okay, so everybody, some experienced more steep drops, okay, but everybody experienced a drop. Nobody experienced an increase. Okay. All right. And so now that we have just one sample, okay, our standard error is going to be the standard deviation of the difference divided by the square root of n. So in our case, we've got 0.629 divided by the square root of 8, okay? So this leads to 0.2224, okay? And then your test statistic, which is a t-value, is going to be the mean of the difference column divided by your standard error. Okay, so we're going to do 1.15375 divided by 0.2224. Okay, and we get a test statistic of 5.188. Okay, and our degrees of freedom, now that we only have one sample, n minus 1, we have 7 degrees of freedom. Okay, so kind of treat the data as having only one sample. Okay, so we'll go, oops, something happened. We'll go to the t-table. We'll look at 7 degrees of freedom. We'll look up 5.188, and we're between these last two columns, 0.005 and 0.0005. So our tail area, look up 5.188 in the t-table. Okay, and we get tail area between 0.005 and 0.0005. And so this means the p-value is between 0.01 and 0.001. Okay. And so this means we would reject the null hypothesis at alpha equal to 1% and also at alpha equal to 5%, right? So we would reject. And our conclusion would be we have evidence that the mean difference mu d is not equal to 0. Okay, and in fact, we have evidence that it is greater than 0. Okay, and so we would say we have evidence that, you know, caffeine does make a difference at myocardial blood flow, even at the 1% level. Okay, how do we know it is not 0? Well, our null hypothesis was that the mean difference is 0. And if the mean difference is 0, we would expect our D bar, our average of this difference column, to be close to 0. The average of our difference column is 1.15, which doesn't seem big, but compared to the standard deviation and compared to the standard error, it is quite big. A difference of 1.15 is, you know, over 5 standard errors away from 0. And so therefore, this number that we get, 1.15, is significantly different from 0. Okay, and so we know that we can reject the null hypothesis, right? We reject the null hypothesis at the 1% significance level. And that gives us evidence that in favor of the alternative, that the mean difference is not equal to 0. And if we look at the data, our mean difference is indeed greater than 0. It's going to be positive, indicating that the usage of caffeine results in a drop in myocardial blood flow, okay, based on these 8 subjects. And it was consistent across all 8 subjects, and therefore, you know, we're comfortable generalizing to the population. Okay, let's see. So the question asks, all right, so I got a couple questions here. One says, do we reject the null hypothesis due to the mean, or do we reject due to our p-value? Right, so we use the mean to get our test statistic, and then with our test statistic, we get our p-value. And we use the p-value to reject the null hypothesis. The p-value is less than 1%. So if alpha was 5%, if alpha was 1%, we're going to reject the null hypothesis. Okay. Question was, couldn't we have just rejected our null after calculating the mean difference from the column, since that it was not equal to 0? So this number is 1.15 and it's not 0, but that of itself is not enough for us to reject the null hypothesis. Okay. We have a couple questions on how we got this standard deviation. Okay. the standard deviation, sorry, I should have just reminded you, the standard deviation, this is just a matter of plugging into the formula. S is equal to the square root of the sum of, y minus y bar squared over n. I got this, I just basically, you could do it by hand, but when you have R, why would you bother? So, you could just create a vector and you can type in these numbers, 1.85, 0.25, 0.88, 1.6, 1.05, 1.67, 1.74, and 0.33. And then you can ask standard deviation of X. And then we got this number, 0.629. You guys can see that. Okay, so the standard deviation, I just used the calculator or the computer. I typed in the numbers in that column, and then I said, give me the standard deviation of that set of numbers. Okay, but this is it's just the result of using that formula, right? You calculate the mean, you subtract the mean off of every number, you score those numbers, you add them up, divide by n minus 1. Okay. So you can use R to calculate the standard deviation there. Okay. Does that make sense? I forgot what the view quiz answers are. Let me look up today's view quiz answer. Okay, the first view quiz answer is the letter E. E as an elephant. E as in elephant is the first view quiz answer. Let me jot down what the other numbers are so I remember. Okay. It's week 4. All right. E as an elephant is your first view quiz answer. All right. Are there any other questions? Does this kind of make sense? All right. And the key here, again, because you'll see this question. We're treating it as we almost have only just one sample, okay? And so you only have one mu in your hypothesis, okay? It's not correct to treat it like you have two separate mu's. We're really only interested in the difference. Okay. Then I will continue on here. And we'll make a confidence interval. For the mean difference, okay? Confidence interval for mu d, right? The mean difference. Okay, versus, let me just write, as opposed to confidence interval for mu1 minus mu2, the difference between means. Okay, so we've learned how to create confidence intervals for this quantity, mu1 minus mu2, back when we did chapter 6. And today we're doing a confidence interval for the mean difference, right? So again, kind of step 0, I guess, would be find the column of differences. And then calculate the mean. which will denote D bar, and calculate the standard deviation of the differences, which we will denote S subscript D. Okay. All right. And then, so once you've done that, so we've actually already done this. So from the previous slide, we have the mean difference, D bar, is equal to 1.154, and the standard deviation of differences is 0.629, and the number of differences, I guess, is 8. Okay, and then so your confidence interval formula is basically the same as a confidence interval for one sample. All right, and so we're going to put the mean D bar in the center, plus or minus critical value T multiplied by the standard deviation of the differences divided by the square root of n of those differences. Okay, and then critical value comes from the T table. Degrees of freedom equal to n minus 1, number of differences minus 1. All right, so let's try it out, right? So let's make a 95% confidence interval. For the mean difference, 95% confidence interval. Okay, so we'll do 1.154 plus or minus, and the critical value we'll look up spacebar here. 7 degrees of freedom, 95% confidence. The critical value is 2.365. Times 0.629 divided by the square root of, and I get 1.154 plus or minus, let's go ahead and punch this in, 2.365 times 0.629 divided by the square root of 8. We'll get 0.526. So plugging that in, 1.154 plus, or we'll do the minus first, 0.526. This gives me 0.628. To 1.154 plus 0.526 gives me 1.68. All right. So I would say I am 95% confident that the mean change in myocardial blood flow from baseline to caffeine is between 0.628 to 1.628, I don't know, units lower. All right, so the mean change. So because change is defined, or the difference, I should say. Difference was found by taking the baseline minus caffeine. So if we're going from baseline to caffeine, the caffeine numbers are lower, and that's why we're getting these positive numbers, because the caffeine values are less than the baseline values. If we had reversed the order, caffeine minus baseline would have got negative numbers. Okay. And again, we're talking about the mean change or the mean difference. Okay. Maybe I will note and I'll say, do not say, okay, do not say, and this is what we would have said if we had two independent samples, would be to say something like, I'm 95% confident that the mean baseline value is between 0.628 and 1.68, units higher than the mean caffeine value. Okay, so this is wrong because, or this is incorrect because it's referencing two separate means, okay? References having two separate or independent means. Okay. Does that kind of make sense? And I don't think I need to do like a whole slide on like interpretations of the confidence interval, right? Like if we said, do we have evidence that the mean change is greater than 0? You would say yes, because 0 is not inside the interval. Or do we have evidence that the mean change is different from 1.5? We would say no, because 1.5 is inside the interval. Like I can skip that, right? Or do you want me to write that down? Okay, someone gave me a thumbs up. I'm gonna assume that means I can skip it. I'll just write one example. I'll just write all the familiar. Okay, can we write it for review? Okay, so I'm gonna just write it real small here. All right, so I'll say, do we have evidence that mu d is different from 0? And the answer is yes. 0 is not inside the interval. Okay, or do we have evidence that mu d, the mean change or mean difference, different from 1.5? Okay, and the answer is no. 1.5 is in the interval. It is a plausible value. Okay, I hope that's good. And then, of course, you know, all of the other interpretations that we have for confidence intervals. And again, it's basically a confidence interval of one sample, but it's one sample of differences. And we're asking about the mean difference and things like that. Okay, so that is the confidence interval for the mean difference and the paired t-test. Okay. And now I'll do a couple non-parametric tests, the sign test and the signed rank test. Okay. So let's do the sign test. Okay, and so this would be this is a non-parametric test. Okay, so no distributional assumptions are made about the sampling distribution. Distributional. Okay, so we have no distributional assumptions about the sampling distribution, but kind of the in general, it's weaker or has less power than the paired t-test. So this means a few things. There is more prone to type 2 error, the false negatives. Okay, and basically requires stronger evidence to reject the null hypothesis. Okay. Sometimes the sign test is useful if you have incomplete measurements. Okay. I'll say may be necessary, may be the only option. If you have incomplete measurements. Okay, so let's try an example. Why don't we just use this? That's not the picture I want to copy. Let's just use the same example that we've been running. Okay. All right, and so the way the sign test works. Okay. Is basically you look at whether the change is positive or negative. Okay, so you just write down the sign of the change. Okay, so you'll just do kind of you'll say positive if y1 is greater than y2, negative if y1 is less than y2. All right. So we'll go through and we'll list off all of these changes. Okay. So this is a y1 is greater than y2. So over here, y1 is greater than y2. Here, y1 is greater than y2. 5.2 is greater than 3.81. 5.11 is greater than 4.06. 4.89 is greater than 3.22. 4.7 is greater than 2.96. Okay, so this is not an interesting result, but you will end up with the number of positives, which will be the number of positive differences, n plus. And then you'll have n negative, the number of negative differences. Okay, so we have n positive equal to 8 and n negative equal to 0. Okay. And then what we'll do is we'll go to the sign table to get kind of the corresponding p-value. Let me actually write what the hypotheses are. Now the hypotheses, unfortunately, for the sign test is you have to write these long, wordy, long-winded sentences here. Okay, so we're going to say the distribution. The null hypothesis will be that the distribution of differences, which is calculated as baseline minus caffeine, okay, is just as likely to be positive as it is to be negative. So we're basically saying that if you take a difference baseline minus caffeine, it's that number, whatever you get, is just as likely to be positive as it is to be negative. It's not going to favor positive values. It's not going to favor negative values or something like that. Okay. A non-directional alternative will be something like saying the differences again, baseline minus caffeine. The differences are not equally likely to be positive and negative. As they are to be negative. All right, and this is not specifying one over the other. All right, and then you can have directional. It could be saying the direct differences are more likely to be positive. Basically saying that the baseline numbers tend to be larger than the caffeine numbers. Okay, or you can have the other directional, right? The differences are more likely to be negative. So these are kind of your options for hypotheses. And again, when you have a non-parametric test, we don't make any references to things like the mean or some kind of parameter. Here, we're just talking about the differences directly and there's the sign of those differences, whether those differences are more likely to be positive or more likely to be negative. Okay, so anyway, you just basically go through and you say, are the differences that we've seen positive or negative? And here we have 8 positive differences. We have 0 negative differences. And then we go and look this up in the sign table. So inside your we have the Cox and Mann-Whitney table. We have where is it? Critical values for the sign test. Okay, table 7, critical values for the sign test. Okay, and so now we basically go and we say, all right, how many values do we have? Okay, we have 8 values in our sample. And really, you only get kind of a significant value based on whether you have 7 or 8 if your value, okay? So the test statistic is going to be the larger of n plus or n minus, okay? So the test statistic BS is equal to the larger of n plus or n minus. So in our case, BS is 8, okay? And we look it up in the reference table. Reference table 7, I guess. All right, and so this test, when you read the table, okay, you have to read the heading, okay? It says, because the sign test null distribution is discrete, this table provides selected values of the test statistic in bold type and corresponding p-values for a non-directional alternative in italics. Directional p-values are found by dividing the numbers in italics in half. All right, so here we have, I'm assuming we're going to just start off with a non-directional alternative. So the p-value for a non-directional alternative okay, when we go to the table, we have 8 observations. Our critical value or our test statistic is 8. And so we get 0.008 and it's repeated multiple times in this row here, but our p-value is 0.008, okay? If we chose the directional alternative, okay, again, we would have to choose if the direction of our alternative aligns with this, we could take our p-value and divide it by 2, get 0.004. If the direction does not align, we would just say we don't have evidence to support, the wrong direction, right? If we had said the differences are more likely to be negative, right? That the caffeine numbers are going to be higher than baseline, right? That the difference is if we do baseline minus caffeine, if we said those differences are more likely to be negative, we would take our data and we'd say, yeah, we have no evidence to support this, right? The number of positive differences is much larger than the number of negative differences, so we have no evidence to support that alternative. All right, we have a question. It says, did you mention how we know which column to use on the table? The columns in this table are, I don't know why they have these columns. They're trying to pick, so it's especially weird when you have something like 8 observations and they're just basically trying to pick statistical values that are close to these numbers, okay? But these values, right, when you look at how many positive or negative differences you can get, if you only have 8 observations, you're either only going to get like 6 positive differences, 7 positive differences, maybe 8 positive differences, but you'll never get 7.5 or 7.4 positive differences. And so you can really only have 7 or 8. And so the probability of getting 7 positive differences is around 7%, which would be significance at the 10% and 20% level. The probability of getting 8 positive differences is 0.008, and that would be significant at the 5%, 2%, and 1% levels of significance, okay? And it's, you know, if you had a alpha, right, of 0.001, okay? You will never get a value that's significant at the 1% level, because that's not going to happen with 8 observations, okay? But if you have a much bigger sample, say 20 observations, okay? At 20 observations, if you have 14 positive differences, that's significant at the 20% level. It's not, your p-value is 0.115, which is significant at the 20% level, but not significant at the 10% level. If you have 20 observations and you get 15 differences, 15 positive differences, that would be significant at the 10% and the 5% levels, okay? And then if you want to be significant at the 2% level, you need 16 positive differences. If you want to be significant at the 1% level, you need 17 positive differences out of 20 observations or something like that. I don't know, does that kind of answer your question, I hope? All right, we have another question. It says the ND value on the table for this example was 8. And for looking for our values, the value is also 8 due to the number of, So ND is just the number of differences, right? So we have 8 subjects. Each subject had kind of 2 measurements, but really we're just looking at whether that difference is positive or negative. So the number of differences that we have is 8, okay? And in our case, all 8 of those differences were positive. And so our n plus is 8. We have an n minus, which is 0. And we use the larger number to determine our test statistic here. Let's do another example for the sign test. I hope that will clear up some questions. And this is an example where you have, this might be the only option because we have incomplete measurements. So let me pull up our online textbook here. Oh, let me give you your second view quiz answer. Second view quiz answer is the letter C. The letter C, C as in cat. C as in cat. It's our second view quiz answer, okay? All right, so this is all right, let me just do a new slide here. Okay, all right, so this is the example from the textbook. And this is a bit of a morbid example, but you know, sometimes, you know, patients will arrive in the hospital, you know, you have burn victims and they need skin grafts. And they said, you know, sometimes skin from cadavers can be used as a, you know, to provide temporary skin grafts for severely burned patients. And the longer such a graft survives before its inevitable rejection by the immune system, the more the patient benefits, right? So we want the skin graft to survive as long as possible before it gets rejected. And they are looking at, they're investigating the usefulness of matching a graft to the patient with respect to human, I don't know how to pronounce this, leukocyte antigen, the HLA antigen system, okay? And so I guess the people who participated in our study, they received 2 grafts, okay? One that had good, close HLA compatibility, and the other, they also received another skin graft with poor compatibility. So yeah, I guess I'm sure they had to get consent from the patients to participate, and they said, hey, are you, we're going to do some skin grafts. Are you willing to let us try out this experiment? And we're going to try one with good compatibility and one with poor compatibility. And then they measured the survival time, okay? How long that skin graft lasted and as far as number of days, okay? And this is the data that they've obtained. So we had 11 patients, okay? And these are the numbers. Now, some of these numbers, okay, we did not get an actual reading for, okay? See this plus, 57 plus means, our study ended, okay? So 57 plus means the study ended. So we don't know when it got rejected, okay? The study ended at kind of 57 days. And, the survival time, whatever it is at least 57, right? It's at least 57. It could be 58. It could be 95. It could be 150. We don't know. We just know that the number is at least 57. Same thing with this measurement. This person, the poor skin graft lasted 42 days, but the close match skin graft lasted at least 60 days. We don't know. How long it lasted, but it lasted at least 60 days. Okay, and so here they took the sign of the difference y1 minus y2, and they already gave us pluses and minuses. Okay. All right. So the number of positive differences is 9. The number of negative differences is 2. Right, and we have the number of our observations. We have 11 patients. Okay, so in our case, we have a null hypothesis, and we're going to say we expect basically, the probability of positive, right? The difference is just as likely to be positive as it is to be negative. Okay. And then the alternative is directional. And we're basically saying we expect the close match to last longer than the poor match, right? Which basically means the differences, the sign of the differences are more likely to be positive. Right? If we expect the close match to last longer than the poor match, the differences are more likely to be positive. Okay, and our data does indeed match the directionality. Because the number of positives is greater than the number of negatives. Okay. Oh, we have 11 because we have 11 patients. We have a total of 11 plus or minus signs. Okay. So our data does match the directionality because n plus is greater than n minus. And because we expect more positive values, we use n plus as our test statistic. Okay, so more positive values, you know, this, because I guess our, we expect from the alternative hypothesis, we expect more positive values. We're going to use n plus as our test statistic. Okay, so we will go to the table. All right, so we go to table 7. ND is 11. N plus our test statistic BS is going to equal 9, right? And so from our table, 11, 9, our non-directional, right? So again, we read these and we say the non-directional p-value is 0.065, okay? So ND is 11, number of observation is 11, number of differences is 11. The number for our test statistic is 9. We have 9 positive differences and we have 0.065, okay? Is our non-directional p-value. Okay, so that's just from our table. 11, 9, 0.065 is our non-directional p-value. Okay, so our alternative, our HA, is directional. So our p-value is going to be half of that. Okay, so I get a p-value of 0.0325 if alpha is 5%, our p-value is less than alpha, and we reject the null hypothesis. We have evidence that survival time of skin grafts with a close HLA match last longer than skin grafts with poor HLA match. All right. Sometimes, and we didn't do an example, but sometimes y1 equals y2, right? And the difference is 0. Okay, 0 is neither positive nor negative. Right. So sometimes you ask, you know, what's the sign of y1 minus y2? Sometimes you get 0 for the difference, right? If the before and the after is the same measurement, sometimes there's no change or something like that. Okay. So in these cases, basically you just throw that out, you just ignore that observation, right? So in these cases, we basically ignore that observation. Right? And we reduce ND to the number of non-zero differences. So if, you know, if one of these, you know, we had no difference, like if observation 11 was a tie, 18 and 18 or something like that, then we would just say ND is 10, okay? We would just say we have 10 differences or something like that, okay? And then, and you would have, you know, you'd have a different whatever, n plus or n minus, whichever one or something. Okay. So sometimes that happens. All right. So it's important not to treat a 0 as a positive number or 0 as a negative number. It has no sign. 0 has no sign. Okay. Are there any questions here for the sign test? We'll feel good. All right. Okay. Then let's do our last test. And this is going to be the Wilcoxon signed rank test. Okay. All right. And this is, again, another non-parametric test. Okay, but it's more powerful than the sign test. Okay. So here I'm going to use another example from our textbook. Okay. So here is, let me copy this. Let me just read the okay, so they I guess they're looking at horse anatomy, all right, and they're looking at 9 different horses, okay, and it says a veterinary anatomist measured the density of nerve cells at specified sites in the intestine. So I guess inside the intestine, you have nerves there, and they have results for site 1, the mid region of the jejunum, I don't know, and site 2, a different region. So you have one region and another region, and they're kind of comparing the nerve cell density at these things, right? And so they look at this and look at that. They've already given us the differences here. Okay. So, you know, basically we have 9 observations or we have 2 measurements on basically the same 9 subjects, right? So we have 9 subjects. Each subject has 2 measurements. Okay, and then we basically, we have calculated the column of differences. Okay. All right, and so so here what we do, okay, so step 1, calculate the column of differences we've already done, okay? And then what we're going to do is we are going to rank the absolute values of the differences. From least to greatest. Okay, so basically, so I'll write absolute value of differences in order. Okay, So if I go through, what's the smallest absolute value? I've got 0.2. Maybe I'll use a different color here. All right. So this first one, we'll check them off as we go, okay? In order, we got 0.2. And then what is the next smallest value? Then I got 2.0. And then 2.2. Okay, we're doing the absolute value. So I'm just ignoring the signs. And then the next value is 4.6. And then the next value, I think, is 9.8. And then the next value is 10.8. And then the next value is 12.0. And then 12.6. And 20.6. All right, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I have nine values. Okay, and then and we're going to rank them. Okay, so I will I'll just do ranks of the absolute values. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I put them in order from least to greatest, and then I rank them from 1 through 9. Okay, so far so good. All right, and then we go back, right, and we pick out the then find apply signs to the values. Okay. All right, so rank the absolute values of the differences from least to greatest, right? And then 3 will be apply signs. Apply signs to the ranks. Okay, so this is why it's called the signed rank test. So we're going to say, okay, we have 3 negative values. We have negative 2.0, so we're going to apply a negative sign to that rank. We're going to apply a negative sign to this rank. And 0.2, we're going to apply a negative sign to this, right? So these are the 3 negative values, and they happen to be 1, 2, 3, okay? But if 20.6 was negative, we would apply a negative sign to 9. Okay, so we're just going through and we're saying, okay, which differences were positive and which differences were negative, and we're going to apply negative signs to the ranks. Okay, apply signs to the ranks. So 3 values were negative. Negative 2.0, negative 2.2, and negative 0.2. And so we apply minus signs or negative signs to their corresponding ranks. Okay, and then what we do is we sum up basically the positive ranks, and you sum up the negative ranks. Okay. Sum the positive ranks, sum the negative ranks. Okay, so we'll say sum of positive ranks is going to be 4, basically 4 plus 5 plus 6 plus 7 plus 8 plus 9. And I get, what do I get? 29? No, 39. Hold on. 10, 25, 30, yeah, 39. Okay. And then the sum of the negative ranks basically 1 and 2 and 3, 6 or negative 6. Okay. So those are my positive ranks and those are my negative ranks sum. Okay. And we're going to use the larger sum. The test statistic is the larger sum, and we'll look that up in the signed rank table. Okay, so our test statistic is 39. And we'll go to our critical values for the Wilcoxon rank test. We have n is 9 and our sum is 39. So we're somewhere between 37 and 40. Our p-value is between 0.098 and 0.039. Okay. What did I say? 0.098 and 0.039. Okay. So if alpha were 5%, well, we're in trouble. We don't have an answer there, right? But well, kind of at this table, basically, if you want to be significant at the 5% level, you need to have a test statistic of 40. Okay, and we have a test statistic a little bit shy of that. So we're significant at the 10% level, but probably not at the 5% level. Does that process make sense? What's happened here? Okay. So again, we rank our the absolute values of the differences, and then once you rank them in order, then you go back and you say which one of these differences were positive and negative, and then you basically say, okay, well, these were on the negative side, negative ranks, we add those up. These were on the positive side, and we add those up. Okay. Are there any questions there? I forgot to give you the hypotheses. So the Wilcoxon sign rank test, again, because it's non-parametric, you have all of these like wordy hypotheses. All right, so I'll say hypotheses. So your null hypothesis would be something like maybe say the distribution of values at site 1 is similar to values at site 2. Okay. Or maybe more abstractly, we can also say the magnitude of positive differences is similar to the magnitude of negative differences. Okay. And then the alternatives. So I'll start off with directional ones. Directional alternative will be basically, something like the magnitude of positive differences is greater magnitude of negative differences. Or in other words, site 1 minus site 2 will produce values produce larger positive differences. Okay. And then non-directional would just be the magnitude of positive differences is different, right, than the magnitude of negative differences. Oh, question. Why are we referencing sites as in site 1 minus site 2? That's just from the example in our textbook where they said they measured nerve cell density at site 1, which is the mid region of the jejunum, and site versus site 2, which is the mesenteric region of the jejunum. Okay. All right. That's actually all I have planned for today as far as today's lecture. So we'll end a few minutes early. Let me give you your last view quiz answer. Last view quiz answer for today is A as in apple. A as in apple. Okay. Oh, I guess one more thing. If you get ties, then you average the ranks. Okay, and then if you get zeros, you ignore the observation. If you get a zero difference, so like the sign test, ignore the observation. So let me just do an example of ties. So if you had, so let's say your difference column is something like -12, -12. Here, let's do it. -12, +12, 10, -6, 18, and 5 or something, right? So then in order, we will go 5. So the absolute values we'll have 5, 6, 10, 12, 12, 18. 1, 2, 3, 4, 5, 6, right? So these are the numbers, right? Okay. And then you say, okay, what are the ranks? So we're going to go 1. So the ranks will be 1, 2, 3. And then here we have 4 and 5, right? So you take you average the ranks, right? So this would, I'm going to pencil in 4 and I'm going to pencil in 5. And so the average of 4 and 5 is 4.5. So you'd write 4.5, 4.5, and then 6. Okay. So 1, 2, 3, 4.5, 4.5, 6, if that makes sense. All right. And then when you apply the signs, you go back and you apply the sign and you say, okay, this one was negative and this one was negative. So we're going to give, so to the 12, we will put a negative sign here. And then the 6, we put a negative sign, right? And then so some of the positives would be 1, 3, 1 plus 3 plus 4.5 plus 6. And then the sum of the negatives would be 2 plus 4.5. 10. All right, if that makes sense. This is kind of right. And then again, if you get a 0 difference, ignore the observation, and then ND shrinks to number of non-zero differences. Okay, that's it for today. We'll end here. I'll stick around for office hours as usual. Otherwise, have a good night, and we will see you guys on Wednesday.